Hello, welcome back. Happy New Year. So, today we'll be continuing our work, continuing our journey on to understanding the control of the half-bridge converter and how we can make it more efficient. So, previously, what we saw was we saw the implications of the feed-forward compensation in the controller, and the first in the last video we saw the first advantage of using the feed-forward compensation control, which was impact on the startup transient. Basically, it was mitigating our it was mitigating the startup transient that we saw in the current, which was basically loading our converter initially. This huge negative current flowing from the source to our converter initially, and as soon as we added to the feed forward compensator, or the information of the AC system to the output of our compensator, we saw that initial transient was mitigated very effectively, and we got our desired results. Now, in the second advantage we will see of the feed forward compensation is the independent or the decoupling of the dynamics of the AC system, a realistic AC system, to the converter system. So what I mean by that is, this is our typical AC system, which as of now we were just representing it by a voltage source. We're giving it a 400 volts of voltage, but here we will have some inductances, some capacitances. These are all system impedances, and which will basically represent a realistic AC system, has its characteristics, and we'll try to model this in our model and see what happens, what impact this realistic AC system has on the dynamics of our converter control. We'll see what happens to our currents, our voltages with this realistic system without the feed forward compensation control, and we'll see what impact our feed forward compensation will make to those various oscillations, to those various impact of this AC system, and how it decouples, how the feed forward compensation decouples the dynamics of the converter system and the AC system. Now we'll see the example, and the example says, so we'll try to model our system in this way. We have the LF, CF, RF values, and we'll take this example 3.3. Now let's go to our converter. So let's see, R value is the same, L value is 450 microhenry, so let's change this to 450. Then we have VS or VTH, so let's just change the namings. Okay, and then we have an inductor in the series with the source, so we paste this. L, this is 250. Okay, and parallel to that we have a parallel RC branch, so we'll take parallel RLC branch, open it to convert it to this. We have R as 50 and capacitance is 2500 microfarad. Alright, okay, this is our VS, this is our VTH 400, and then what else is changed? So the switching frequency has changed now. It has increased to, I guess, double the one we were using previously. It's more than double, so we'll change this to 3780, and also we'll change these measurement frequencies. Alright, okay, also we have the KP and KI changed from the previous values. We had 0.15 and this is 1.96, right? Okay, and let's just remove our feed forward compensation. We'll see how the system behaves without the feed forward compensation, what implications or what changes or what oscillations we see in our current and voltage waveforms with these new with these new characteristics of our AC system. I'll run this. Okay, so we get that new and let's see, let's zoom in here. So this is what we see. So what's happening here is we see these oscillations in the current in as well as the source voltage. So what is guiding these oscillations, or what is the main reason of these oscillations are that our control is still is just seeing the current. Okay, it doesn't have any information of the AC system. Now what we see is here we have a very poorly damped oscillatory modes of the AC system, as also mentioned in the example that with when there is no feed forward compensation, when we change the VS experiences a low frequency oscillations due to poorly damped oscillatory modes of AC system. The oscillations lead to a poor transient response of I. What it means is that this AC system, what we have here, has very poor damping for the voltage which we see here, which is the source voltage. You can see it here as well. So this is the source voltage. So this is our source voltage here, and because of that very poor damping of that voltage here, we see very poor oscillations damping in the current as well. So that's the main reason why we see these oscillations. Due to these oscillations in the voltage, we see the current also oscillating. Now what if we have the information of the AC system and we manipulate our controller in such a way that it knows that these are my characteristics of the AC system. It has very very poor damping characteristics, and you take that into account and reduce the oscillations in my power or my current. So how can we do that? So here comes the second advantage of the feed forward compensation. That is, it will just decouple these both converter system and the AC system. With the knowledge, decouple the dynamics of these two systems by having a prior knowledge of the characteristics of the AC system. Now what if we add that 400 again? If we add that 400 again here, like what we did in the previous section, we will see, obviously what we'll see is that initial transient will go away. That initial transient must go away now. Yes, so the initial transient went away. It was going from 2.5 kiloamperes. Now that initial transient has left our screen, left our system. Okay, good for us, but we still have these initial oscillations oscillating with the amplitude of 500 amperes. And when we see the step change here, also we'll see those as oscillations. Now okay, you have given that information 400, all right, okay, you gave that information from here, but what about these other information? The source, we basically put the source voltage here, right? Now to give that extra information, what we'll do is, instead of giving that 400, just leave it here, what we'll do is we'll give the information at this node, which is our initial, which is basically our the source according to or as seen by our converter system. So by calculating the voltage here, taking into account all these characteristics L, R, C and everything, and writing the equation for the VS here, which has a dependency on current, we'll try to form this the equation. And I already did that calculation, I already did that derivation, and what I come to, what conclusion I came to is, or what equation I came to is this is the last equation that I came that came out from my derivation. And what you can see is a strong dependency of VS on I, and various integrals or double integrals of Vs and Vth. Now please write in the comment if you need the full derivation of it, but it's very easy. You guys can try it on your own and come to this result here. Now what I'll do is I'll try to give this information to the output and add it to the output of our compensator here. So what we need is we have to give this information, we'll have to design this system. This is our AC system. This is what I'm talking about. So with the current that you have, you'll derive a VS in a control format with the information which will carry the information, which will have all the information of the characteristics of the AC system, and that will add basically after a feed forward filter. Obviously will add to the output of our compensator like we were doing before, as it is done in case of a feed forward compensation. Now so basically we get a Vs and we get a I. So this relationship is what I have derived, and we can see that in this equation. Now let's just create this in this one. I'll take a constant, let's make it a subsystem, go inside. So this is my output, and the output should be Vs, right? So let's just name it Vs, and there is an input which is I. All right, now what we'll do is we'll first put these into constants. So take constant blocks. So the first one is 1 upon CF, which is 2500E minus 6, right? This is our 1 by CF. All right, now the other is 1 by CF into RF. RF was 50, right? Okay, then we have CF LF. LF was 250 microhenry. So this is my CF LF, and last is 1 by LF. Okay, so these are 4 constants, and then we'll have integrator blocks. So integrator, so the first one is integral of I multiplied by 1 by CF. So let's take product. Oh, you can take the gain blocks as well. These could be gain blocks, and just put them here. I took the constant, so let's just leave it there. So 1 by CF into integral of I multiplied, and then it should be, let's take an add block here and put 2 as positive, 2 as negative, right? You can see this 2 positive and 2 negative. So, and this goes on Vs. So this one goes to positive. The next one should be Vs getting integrated. Vs getting integrated and then multiplied by 1 by CF RF, and then feed it to the negative, right? Then we have a double integral of Vs. So we'll take one more here, double integral of Vs into 1 by LF CF, right? And this should also be negative. And then the final one is 1 by LF into double integral of VTH. Our VTH is 400. Double integral of VTH and goes to positive. Yeah, done. So this is our Vs and this is our current. Current is the measured current, so we'll put it here, and then we'll have Vs added to here. Now this should also, we have a filter too. Let's see what happens without the filter. But in the book it says we have a filter too. Initially we were using 1, but now they've changed it to a different time constant, which is I guess 8 microseconds. Yes, so here they use this as the feed forward compensator filter. So let's see without the filter what happens. What basically we are doing is we have taken our I, we have derived our Vs, and this is our half bridge converter. We don't need to consider this, so we'll just take the Vs and just feed forward it to this part, and this is where we have added it without the filter. As of now, we'll see what happens, and then we'll add the filter and see what happens. Okay, so let's see. Also in this AC system, we will have some the initial values to initialized value to give at the Vs, and those should be given because what I think is here we haven't initialized our solution. So what I mean by that is that we'll have some initial conditions. And what I mean by initial conditions is we haven't given any initial conditions here as of now. We haven't given any initial conditions. So what we can do is the initial condition should be the current should be 0, right? But this will start from again, we'll have that initial transient. This is what I mean. So this initial transient we can mitigate by again giving the initial condition at the Vs as 400. So basically this output should initially give us 400. So what we can do is we can also see what happens if the initial output starts from 400 here. Then definitely our the terminal voltage will be initially it will start from 400. But if it starts from 0, then this already is at a higher voltage. Then we'll have some current flowing in kiloamperes or 2 kiloamperes, something like that. We don't want that, but let's see what happens. So okay, so we are seeing that very bad transient here, but let's see the situation. Yeah, so if you see our step response is more efficient. It has beautified it. Our compensator, we have designed it very well, and we don't see those oscillations that we were seeing before. Still we haven't put the filter yet, but the response is very good. We don't see those oscillations in the current. Now this system, we can say if we ignore the initial transient because it doesn't look very good, but the step response, as I see, there could be some small oscillations. We don't in the current we can see them, but from what we had before, we see that the system has improved a lot. Now let's connect that filter. So we'll take a transfer function, add it here. This should be 8e minus 6, right? Okay, now let's see what changes it makes. We still have that initial transient. Yeah, so basically that filter again improves our transient, the transient of the step change. It has significantly improved from what we had before, right? We can see it again. What we can do is just copy this paste it here. We can change this to Q11. This is also Q44. Then these two Q11 and Q44. Okay, and then just remove this and this one and take another scope and just take this current, which is the first one with the feed forward compensation, the second one without. Okay, let's run this. See, we have the initial transient in the one without the feed forward compensation, but with the feed forward compensation we still have this very bad transient. We'll try to see what's the cause of it, but let's see what happens to the step change. Yes, yeah. So the first one is the one with the feed forward compensation. The yellow one is the one with the feed forward compensation, and the blue one is without. And you can see the difference in the oscillations that the steady state, how fast it reaches the steady state, how fast the oscillations get damped when it reaches the steady state, and it remains within the boundaries of our reference current, which is 1000 amperes. So this is the difference that we see, and it has significantly improved with the feed forward compensation. Now what we'll do is for that initial transient, what we should do is that it's still seeing a higher voltage here, and the converter, the terminals of the converter, the voltage at the terminal of the converter starts from 0, and that's why there's a huge current flowing across it, and it has oscillations because of the poor damping characteristics of the AC system. Now to enhance that, what we can do is we can just directly add to the VS 4. Let's see what happens if we add to the VS. Let's put another sign. Wait, so 1 by LFCF and 1 by CFRF. So this should also go in the positive, right? And one more positive, so this is for 400. So this is my initial condition that I gave. Let's see what happens. You can see it here. Okay, we still have that bad initial transient. So let's try to change it. Now what if we add a constant block here with 400 initial voltage? Let's see what happens. Yeah. So our initial transient has been removed now, has been mitigated now, and let's see how our system behaves at the step change. So what we have done is that, okay, this system will give me the characteristics of the AC system, the information of it, and feed it to our compensator. Give the change in the terminal voltage, to mitigate those oscillations due to the damping, the poor damping characteristics of the AC system. And this 400 will basically give the initial condition to our converter that you make this much amount of terminal voltage here. You make this much voltage at your to start the system from a current 0 without loading our converter, right? So let's see. Yeah, so this is much better now. And if you see this this is our step response, and the current waveform looks very beautiful, right? Beautiful from the one we see here. See, it has the initial transient as well, and it has these oscillations. See, this is the initial transient in the one without the feed forward compensation. The yellow one is with the feed forward compensation. And if you see the step response, you can see the blue one basically going out of our limits and very slowly damped. It has a very poor steady state characteristics, and these oscillations basically are not healthy for our system. But in the one with the feed forward compression, the yellow one looks perfect, looks good. I think that's all for today. So what we saw was that today we saw another implications, another advantage of using the feed forward compensation, which was decoupling the dynamics of the converter and the AC system, right? With if we have all the information of the information and the characteristics of the AC system, we can feed that. That's why from an industry point of view, we have the short circuit levels of the AC grid. We have the minimum, maximum, the extreme minimum short circuit levels of the grid. We derive the system impedance through them. We have the short circuit ratios. These all are the information of the grid, and as much information as we can have of the grid, how weak it is, how strong it is, how it behaves, how the damping characteristics are, we can feed this information to our controller, give it more information, make it more efficient with this information, and get very efficient results like what we saw in our results in our model. So that's all for today. Let me know if you have any doubts in the comments. I'll try to answer them as soon as I can.